with that, thank you, Thomas.
Yes. Well, first of all, I guess thank you so much for Simon Duckett to give such a wonderful talk about the discovery of SABRE and its mechanisms. I very much enjoyed it. So thank you for that. And also now towards the SABRE-SHEATH, I want to, of course, thank all my collaborators that have helped me along the many years and the many years to come, obviously. In my talk, it's my goal to first kind of tell you a little bit about the historical development of the discovery, why it makes sense to conduct SABRE inside of a magnetic shield, and really to illustrate how there's also luck involved. And sometimes, you just have to have the good fortune to kind of understand what you're doing. And then I want to kind of talk about the underlying mechanism. So I want to kind of do a little bit of a tutorial on sort of the spin dynamics that are involved in the SABRE transfer. And then I do kind of want to take advantage of this opportunity here to highlight some of the sort of most recent work that we're doing right now in my lab, but also in Edge Manev's lab. So that'll be concluding this talk. So first, once you've done some fun work and you're getting ready to write a paper, of course, one of the fun things to do is to come up with an acronym. I do hope that coming up with the acronym SABRE was just as much fun as coming up with the acronym SABRE-SHEATH, standing for Signal Amplification by Reversible Exchange in Shield enables alignment transfer to heteronuclei. And certainly I had two or three laughs when coming up with this silly acronym. So I just wanted to share that briefly. So here's a video of how SABRE-SHEATH works. It's pretty simple. Parahydrogen is bubbled through an NMR tube. The SABRE solution is in there. As we learned from Simon how to make SABRE solutions, it can be put into a magnetically shielded environment, and then we have a coil inside that just very carefully tunes the magnetic field to the right microtesla magnetic field. We bubble for, say, 30 seconds, transfer, for example, into a benchtop NMR spectrometer. This is a National 15 system, and we acquire, for example, here a National 15 signal with 10,000 to 100,000 times more signal than you would usually get from a National 15 signal. So in a benchtop system like this, National 15 at these concentrations, you would never be able to see. But now, after having briefly placed the sample inside of this magnetically shielded environment, you can get very, very good signals. And so I want to kind of look at the history a little bit of how this got developed. And obviously, as we just saw from Simon Duckett, it all starts in his lab, 2008, 2009, where they developed these various approaches. And I think it's really quite remarkable. And so Simon Duckett pointed this out, that one of the first papers that he published is this inept SABRE, where he hyperpolarized Natrium 15 directly in the magnet. And of course, inept can be implemented at any magnetic field, so that it opens up a lot of opportunities. But then, of course, there's the two most famous articles, the JAX article and the Science article, also both in 2009. And I first learned about SABRE at the ENC in 2009, where I was still in Alex Pines' lab, trying to kind of still figure out really what to do with my PhD and what are the most interesting experiments. But this obviously was very exciting. And so going back to the lab, I was working on Zero-Field NMR. And so I was kind of wondering if one can maybe do SABRE and detect it with Zero-Field NMR. So here's kind of the fun part about SABRE. SABRE can be made to work at any magnetic field, and it works better at some and not so good at others. There's zero field, microtesla field, millitesla fields, and then obviously high magnetic fields. In terms of the development, obviously there's this inept SABRE paper from Simon Duckett, 2009, and then at the millitesla fields, also 2009. And then I implemented this at zero magnetic field in 2012. And then in 2014, we realized that we could take advantage of this and also you know, hyperpolarize it in a shield, but then actually detect in a high field magnet. So that's SABRE-SHEATH. And then the work that enabled hyperpolarizing long-lived singlet states directly with SABRE, that I'll also briefly touch on and explain the mechanics of it. So at zero magnetic field, an inductive coil is of course not very sensitive. And so if you want to detect a signal at zero magnetic field, it's better to use maybe a magnetometer that is sensitive at low frequencies. And this is kind of work at the end of my PhD thesis. And after having seen Simon's work, we were then trying to basically obtain SABRE hyperpolarization in a magnetically shielded environment. So you can see all the shields on the left that really get you down to a magnetic field where the proton frequency is maybe 0.1 hertz. So from the proton's perspective, really no frequency at all. And then there are magnetometers that you can operate in a pump probe mode with lasers to detect your NMR signals. I won't bother with the details at this moment. And I kind of want to just briefly illustrate how silly we were in the beginning when we were trying to do this. I saw Simon's work, and obviously it worked well at 6 millitesla, 7 millitesla. So we tried in these systems to hyperpolarize, to build a coil. We built a coil that produced 7 millitesla field to then try to produce hyperpolarization, and with a pneumatic shuttle to shuttle this NMR tube down after hyperpolarization to then detect the hyperpolarized signal with the rubidium vapor cell, the detector in the middle of the magnetic shields. But then, while we were doing the experiments, we noticed that actually not shuttling the system at all and just bubbling in the shield, which was kind of unexpected at that point in time, actually gave us much, much bigger signals. So what's happening there at zero magnetic field? It's kind of really funny in that you start out with parahydrogen in its singlet state. It's a spin order that you have. It binds to the iridium catalyst. And now the spin order can propagate through this exchanging system onto, for example, nitrogen-15 labeled pyridine. And it creates sort of scalar order everywhere. It's important to remember there's no magnetic field there. So there's no alignment. There's no sense of direction. And so the only thing you can possibly get is kind of singlet state order everywhere. And that's what you generate at zero magnetic field. Then we apply a short pulse of DC magnetic field. That short pulse gives the system a direction, something to think about. And the spins can propagate around that magnetic field. It breaks all these singlets apart, and then we can actually detect the signal. So for example, if you do that and there's absolutely no magnetic field on during acquisition, then all the interaction that you have are J-couplings. And that means your spectra that you acquire are dominated purely by J-coupling. So in the case of nitrogen-15 labeled pyridine, we see, for example, peaks at 3/2 times the J-coupling, which in this case is on the order of 16.5 hertz. And the J-coupling between the nitrogen-15 and the proton is on the order of 11 hertz. So that's kind of how these things add up. So then, when I was working at the Warren Lab at Duke University, I had the great fortune to do a short stint with Ed Checkmanev. And we were actually trying to develop something similar to the inept SABRE, namely the light SABRE pulse sequence, where we were trying to irradiate with very low power pulses to get SABRE working at high magnetic field. However, at the beginning, we didn't know where the nitrogen-15 signals were, so we didn't really have an idea of how to probe the system. And so then I kind of, in the moment, it felt like a silly idea to take a magnetic shield, stick the sample in the magnetic shield, and because I knew from the zero-field experiments that sometimes that is successful in giving nitrogen-15 hyperpolarization. We did that, we stuck it in the shields, and then back into the magnet. So it's basically the upside down experiment of the zero field NMR. And a huge signal emerged from that experiment. And my great fortune was that Ed Checkmanev was right there watching me do my silly things. And he recognized immediately the value of the SABRE sheath that I had not fully comprehended in that very first moment. And thanks to Ed, then we were able to, publish many papers and really kind of drive the SABRE sheath method forward. So here's kind of some results of the very first attempt. We hyperpolarized nitrogen 15 labeled pyridine, kind of as the standard sample in these shields, and we saw 30,000-fold enhancements of the nitrogen 15 signal. And what we were really looking for were these small tiny signals, the blue one and the red one, the material that is bound to the catalyst, because that's where we wanted to irradiate our light saber pulses onto. But it turned out at the end that this SABRE sheath method is actually much simpler than, for example, a light saber method that requires you knowing exactly the frequencies. With the SABRE sheath method, all you need to do is stick it in this low magnetic field, and then you can also explore many, many more molecules without trying too hard. And here I just want to highlight sort of the difference between what happens if you do a SABRE sheath experiment versus hyperpolarizing the nitrogen 15 simply at 7 millitesla. So the difference is you gain maybe a factor of 3 in signal, and of course that it's all in phase. So it's much more suitable for imaging, whereas something like antiphase signals that you generate at 7 millitesla, they in an imaging application would be rather difficult to deal with, for example. So let's think about the mechanism of SABRE sheath in a little bit more detail. So SABRE sheath is kind of nice because the spin system is a little simpler. It really only involves 4 spins, for example. And the things that we need to think about are the coupling between the 2 hydrides, JAA, for example, the coupling between the 2 nitrogens, JBB, and then, of course, the couplings that drive the polarization transfer ultimately, which is the coupling of the hydrides to the nitrogen 15. In this case, I call them JAB and J'AB. So we can take the spin system and kind of write down a couple of equations to see if we can somehow understand with relatively simple pictures that maybe invoke Bloch spheres, to understand this polarization transfer dynamics in the SABRE sheath experiment. So for that purpose, it's kind of useful to, first of all, think about how we're going to call various states in the system. So you have the spin A and A prime, and so those could be in a singlet state or a triplet state. Then you have the states B and B prime, the nitrogens, and those could, of course, be in a singlet state or a triplet state. So then you kind of combine them and you form a basis of 16 states because they're 4 spins. And those 16 states are, for example, states such as the singlet state, singlet on A and singlet on B, or a triplet on A and a triplet on B. And then there's other combinations such as singlet on A, triplet on B. And the spins, the states that you can connect are those that are of same symmetry. So, for example, you can transfer polarization from a singlet to a T plus T minus state, but you cannot transfer polarization from a singlet T plus state, for example, to a singlet state, or vice versa, because they're kind of symmetry forbidden transitions. They belong to a different symmetry group. So, with that in mind, just one more thing that I want you to be aware of is this difference in J couplings. Delta JAB is the difference between the cis and trans J coupling. That's really the main interaction that drives polarization transfer. And then another important quantity here is the sum of these 2 J couplings, as you'll see, it'll pop up in the equations. So to make such a picture where we can kind of, we're used to thinking about Bloch spheres, we're used to thinking about spins rotating in a circle. So can we kind of use a similar picture to describe SABRE sheath dynamics? And the answer is, if you take the 16 by 16 Hamiltonian of the 4-spin system, you'll find blocks that you can sort of try to understand. So in that Hamiltonian, for example, there's a block like this that connects the singlet state to the T plus T minus state. How is this useful? Well, the singlet state, this is where the parahydrogen comes from. This is where the polarization comes from. and you're driving it, say, for example, into the T- state, you're generating negative polarization on the nitrogen. So what elements are of relevance here? So there's the diagonal elements. Those primarily dictate the distance between the two energy levels. And then there's the off-diagonal elements. Those dictate the driving forces. It's basically the X term. And this is why you can make this picture now, where the X term of the Hamiltonian is minus delta JAB, because that's in the off-diagonal. Whereas the on-diagonal terms, those you want to have close to 0 in the Hamiltonian, because you want to have the X term to be as efficient as possible. So what you need to do is you need to choose a magnetic field at which these two on-diagonal elements become 0. And if you do that, then the density matrix, the initial density matrix, which is hyperpolarized parahydrogen, a singlet, a red singlet, will be interconverted through a rotation into, for example, nitrogen-15 polarization. And that happens when you're exactly on resonance, and that resonance is established when the diagonal elements are equal. So the way you kind of get to this equation that says you're on resonance, you're ready to transfer polarization, is by setting the two diagonal elements equal to one another. There's other cases, for example, this type of case, where it's like two other states that are connected. This is in a different symmetry group, the singlet T plus and the T plus singlet state. Very similar concept. You also drive polarization from the singlet, and then you kind of suck out polarization, for example, from the T plus state here, also eventually generating negative nitrogen-15 polarization. So the resonance condition is just slightly different, but it's obtained in the same way by setting the two diagonal elements equal to one another. So with that, you now have two sort of matching conditions at which polarization transfer can occur, and you can now plug in various values of the gyromagnetic ratios of protons and nitrogens, solve the equation, and you'll find that round about at 3 milligauss inside of a magnetic shield, you can get most efficient nitrogen-15 polarization, the most efficient SABRE-SHEATH effect. And as I kind of said earlier, what is kind of nice about SABRE-SHEATH, as compared to, like, say, any kind of high field methods, is that it's really kind of straightforward. You just make your sample, put your sample together, put it in the shield, and see what happens. And as a result of that, it was pretty easy for us to relatively quickly explore a large range of molecules, all here in this case with nitrogen-15. And so in this table, you also see here in the end, the diazerine as an input. And I guess this is kind of another example of how sometimes one kind of just gets lucky. We were working on diazerines in the Warren lab to explore whether they have long-lived singlet states, but we did not really think about them in terms of being useful for SABRE or SABRE-SHEATH. And so we made a sample of the iridium catalyst, had some of the diazerine in there, and immediately it became apparent that it hyperpolarizes really well, and that we can actually also choose the state of hyperpolarization. We can either hyperpolarize magnetization, so everything aligned, or we can hyperpolarize the singlet order, where at the end, when you do detection, you see these antiphase lines. And so with that, with these systems, we had singlet state lifetimes on the order of 20 minutes, so they could be very useful as molecular tracers. Similarly here, we dug into sort of the underlying Hamiltonians and asking the question, why does the system behave this way? Why do we generate magnetization under a certain condition and singlet states under a different condition? And so if you do this and you kind of write down your Hamiltonian for your system and you look at all the matrix elements that you encounter, you find something very similar. So magnetization, again, is dominated by this connection of a singlet-singlet state to a T plus T minus state, where you can generate T minus hyperpolarization on the nitrogen-15. And exactly as before, the condition for getting this is that the frequency difference between the source, the parahydrogen source, and then the J couplings in the system be 0. For the singlet state in the system, this looks quite a little different, in that you find a term that connects singlet on the nitrogens, the singlet on the protons, the red, to the singlet on the nitrogens. under the condition that the two J couplings between these spins be similar. So again, this was lucky in the sense that diazerine, this is roughly true. The couplings between the hydrides is on the order of 7 Hertz. The couplings between the diazerines are on the order of 16, 17 Hertz. So this transfer was efficient, and we could hyperpolarize singlets at many different magnetic fields. The important part, if you compare the magnetization versus the singlet order hyperpolarization, is that the magnetization, its formation depends on the frequencies, so it depends on the magnetic fields. Whereas the singlet order formation does not depend on the magnetic field. So it really you can form this across a wide range of magnetic fields, the singlet order. And so that's what I'm reiterating here on this slide, is just this point that you have these two kind of resonance conditions. For magnetization, the frequency difference between the hydrides and the nitrogens has to match the J couplings. Whereas for hyperpolarization of singlet order, the two J couplings have to be roughly the same. And we tried Pyruvate in Warren's lab a couple of times, and it never worked. And so I was extremely excited to see, of course, Simon Deckett's work, that he finally got it working. But where the trick is to put the DMSO into this system to modulate the exchange rates in such a way that SABRE would be possible. And also in this system, in the Pyruvate systems, as Simon Deckett very elegantly demonstrates in his paper, you can hyperpolarize either the magnetization on one of the two carbons or the singlet states if you, for example, bubble through the system with a Pyruvate at the Earth's magnetic field. And so I think because Pyruvate obviously is very important for the applications of hyperpolarized substrates, I think this is going to be an extremely promising candidate moving forward. So now I kind of want to transition in my talk to the ideas that we're currently exploring in the lab. So for example, we've been starting to look with SABRE at a lot of drugs, and we have been looking at antifungals, for example. Voriconazole is an example. And here, what is kind of fun is that you have multiple binding sites that can possibly coordinate with the iridium center, and they all act very differently. So as a function of magnetic field, you can see the ones on the 6-membered ring are broader, meaning they have faster exchange, whereas at room temperature, the 5-membered ring has a much narrower sort of field dependence, which means that it is much more tightly bound. And this is reflected also in the temperature dependence of this. So if you change temperature and look at hyperpolarization, you find that at room temperature, the 6-membered ring hyperpolarizes better, whereas at higher temperatures, the exchange is faster, and therefore the 5-membered ring hyperpolarizes better. Another thing that we're kind of currently working on are continuous flow reactors to provide SABRE hyperpolarization continuously. And we're hoping for a live demo that Patrick Tromhon is going to do. Sorry, I kind of need to move the window here, just 1 second. We're hoping for a live demo of this polarization reactor that we have in this little box here. You can see it's like a 2 by 2 by 2 foot box. And what it does when we generate polarization continuously is that we obtain actually RASER effects. So we have FIDs that never go away, they don't decay and just keep going and going and going. Similarly, we can also do, this is primarily work by Ed Shekmanev and Stefan Appelt that we collaborate with. You can do this with PHIP, where we hydrogenate, for example, ethyl acetate, and then we get an Altadena RASER working. So also the lines get extremely narrow, and some really fun thing happens where in the beginning of the RASER, you can see, you can see both peaks, HA and HB on the ethyl acetate. But then as the RASER keeps going, you only see HB because that's the only line that is over the RASER threshold that has enough polarization to give you a spectrum. Similarly, you can do this with gases. So for example, Nuvandi will be presenting his work here with the Altadena RASER and hyperpolarization of propane and diethylether. And another kind of really fun thing I think that we were kind of pursuing is the detection of SABRE in picoliter volumes on the surface of NV diamond centers. So with NV diamond centers, you can detect NMR signals, and with SABRE, with the power of SABRE, we can now go to very low concentrations and detect, tiny amounts of analytes on these surfaces. So this is towards, single cell NMR and looking at the metabolism of a single cell on the surface of one of these NV diamonds. So I hope you enjoy that presentation coming up. So then one other thing we're kind of doing is we're doing DFT calculations to calculate the structures and also the reaction dynamics and mechanisms. So we calculate trajectories of the movement of these molecules, and then we visualize them with AR, so with virtual reality methods, so that now the player or the person that wants to interact with this can go into this virtual reality environment and sort of play with the molecules and look at the SABRE mechanism as it proceeds. And it's all kind of calculated with ab initio DFT calculations. Then work that Echekmenev is pursuing is heavily focused in part on metronidazole, which is an antibiotic drug with very promising applications. And he's very carefully looking at the spin dynamics of what happens if you have multiple nitrogen-15 and nitrogen-14s in your substrates. And for example, here, the role of nitrogen-14 sometimes can be quite detrimental. So this poor guy here running in the back that has a nitrogen-15 in the NO2 group really suffers because the nitrogen-14 sucks all his polarization away and he can't run as fast anymore. And so
Thomas, we are just sort of a couple minutes into the question period. So just so you know.
Okay, this is my last slide. So then finally, Echekmenev is going to talk about whether parahydrogen-induced magnetization could exist on Jovian planets and explain their magnetization. So I hope you'll enjoy that talk and stick around for that. So thank you very much.
That's great. That's great timing too. Thank you so much, Thomas. We have a question about what determines the rate at which spin order transfers into the singlet state, and how do you optimize that? Yeah. So the rate, just from the spin dynamics perspective, is given by this term delta JAB. So it's the difference between the cis and the trans coupling. In the case of SABRE-SHEATH, that J coupling is on the order of 25 Hertz. So 1 over 25 Hertz would be the rate at which this, or 25 Hertz is the rate at which this gets transferred on the catalyst. For the case of normal SABRE, when you have just protons, for example, there the J couplings that you're dealing with are further away and a little weaker. In that case, they're on the order of 1.5 Hertz, and so that will be your rate of spin transfer. So some really interesting questions coming in. What is the motivation behind generating hyperpolarized drugs? Presumably, SABRE processes generate a relatively high concentration bolus, possibly higher than feasible for IV injection, etc. Yeah, I 100% agree. I think that with the drugs, in both bolus injection and looking at that is not the goal. I would say with hyperpolarized drugs, what we want to do is also look at protein drug interactions. So imagine you hyperpolarize the drug in a room temperature solution, and in that solution you also have a protein that interacts with that drug, and you're normally not able to see those interactions between the drug and the protein. So now from a sudden you're in a place where you can in very much detail study the interaction between the protein and the drug. The last question is it known what the relative signs are of the HH and NN couplings in diazerine SABRE? Oh, what are the relative signs of the HH and NN couplings in the diazerine SABRE? I think nitrogen-nitrogen J couplings are often negative. Yeah. This is a question from Malcolm.
Yeah, that makes good sense. I should know the answer, and I kind of know it or knew it. Kind of escapes me a little bit right now. So the proton, the hydride-hydride J coupling is negative, I believe, like around about -7, -8 hertz. The nitrogen proton J coupling, that is on the order of 25 hertz. Yeah, yes, I knew it one time. I forgot right now. I'm sorry.
That's great. Thank you so much, Thomas. We'll thank our speaker again.